첫 번째 세션입니다. IBM 퀀텀의 찰스 청 박사님의 The Path to the Quantum Advantage라는 주제로 온라인 발표가 있겠습니다. This is the first session. Dr. Chung from IBM Quantum will now give an online presentation on the topic The Path to Quantum Advantage.
예, 안녕하십니까. 정찬스입니다. 한국말 잘 못하니까 죄송합니다. 그래서 발표 영어로 할 거예요. So, hi everybody. Thank you for inviting me to speak at this event. My name is Charles Chung. I am the Quantum Industry Applications Lead for Engineering and Manufacturing here at IBM Quantum. Today, I'll be talking about quantum use cases. I'll show you what the current state of the art is and what current trends we're seeing for the future. So first, let me give a little bit of perspective in terms of the activity going on in quantum computing. So investment in quantum computing is accelerating at an unprecedented pace. We have seen over $40 billion of global investment announced for quantum computing around the world. I believe this number is now 55 billion. The customer spend, or the compound annual growth rate, CAGR, is almost 50% per year. And in a survey of quantum computing users, 97% of companies plan to either increase or maintain their investment. Of this 97%, about 2/3 are planning to increase their investment. So these are some remarkable numbers. The reason is, why is this happening and why is it happening now? Well, I believe that there are two reasons for that. One is that business value for quantum computing has been identified, and that quantum computing has reached what we call quantum utility. In other words, we have surpassed what classical computers can compute, at least without approximation. And so I'll talk about each of these in series. I'll first start with the business value, and then I have two short slides at the end demonstrating sort of the technological maturity of quantum computing. So in terms of business value, quantum computing is expected to create a tremendous amount of business value. In a study done by BCG, they predict, or they estimate, that quantum computing has potential to create at least $500 billion worth of value. That's an enormous amount of value. If we look at one level deeper among the applications that are possible with quantum computing, there are three main application areas, and I've listed them here. There are many more, but these are the three that are the most mature, the most well understood, and widely believed to be the nearest term. And I've listed them in chronological order of feasibility. We do believe that chemical and material simulation is the nearest term application. Machine learning is another application area, and optimization of search is the third major quantum computing application area. So what I'll do is I'll talk about each of these application areas, tell you the current state of the art, and again, tell you what the future trend looks like. So let me start with machine learning. What we see in machine learning is that on some data sets, we see increased accuracy. Not on all data sets, but on some data sets. And so this is an example from the European Space Agency. They build this quantum classical machine learning model. They have a couple of layers of a classical convolutional neural net, and then that feeds into a couple of layers of quantum neural net, and then there's an output. What they'd like for this machine learning model to do is classify the images you see on the left. What they're looking for are images taken from satellites that have an image of a volcano erupting. So you see in these 4 images, for example, there are volcanoes erupting. And in these 5 images, there is no volcano erupting. The current state of the art is this machine learning model, classical machine learning model, developed by Del Rosa and et al. It's a 2 million free parameter machine learning model, and you can see its various performances on its accuracy. It's 85% across the board for precision, recall, accuracy, and F1 score. Now, in this paper, the European Space Agency, they executed and trained this hybrid quantum classical neural net, and what they see is an increase of 11% of this proposed hybrid quantum classical neural net, and they see a precision recall accuracy and F1 score at 96%. This is an 11% increase. This is an enormous increase. Second of all, usually when you try to increase, for example, precision or recall, you have to trade one off for the other. If you increase precision, you have to decrease recall, or vice versa. And what we see here is that both precision and recall are being increased simultaneously. Precision is a metric of false positives, and recall is a metric of false negatives. So again, to summarize, the point that I'm trying to make with this slide is that quantum computing has demonstrated increased accuracy, again, on some data sets. Okay, so another characteristic we have observed on, let me point out something else, which is the number of free parameters between the classical and the hybrid quantum is quite different. The classical has 2 million free parameters, and the quantum, or the classical, or the hybrid quantum classical neural net has only 40,000 free parameters, almost a 2 order of magnitude decrease. One of the things that this implies is that simpler models need less data in order to achieve accuracy. And we see that, for example, in this paper. The y-axis here is predicted error, so lower is better. And the error is plotted as a function of the training set size. We have 2 quantum models, one here in orange, one here in blue. And we actually have 6 classical models. Only the best of the 6 classical models is plotted here in green. First of all, you observe that there's a quantum model that has lower error than any of the classical models. But I think perhaps more interesting is that this quantum model is able to achieve the same level of accuracy as the best classical with approximately an order of magnitude less data. And this is important because for most machine learning development programs, the most challenging and the most expensive part of the development is in developing the data set. And so if you could, for example, train your machine learning model on 1,000 data points rather than 10,000 data points, this can be a large savings. So to summarize, we have seen improvements in accuracy and in sampling complexity on some data sets with quantum machine learning. And one of the places where both of these characteristics come together is in what we call something called anomaly detection. Anomaly detection, anomalies by nature are rare, so data is hard to gather. And what we've seen in the among classical machine learning models is they typically plateau in sort of the 60 to 80% accuracy range. Assuming best case, 80%, that's a 1 out of 5 error rate. 1 out of 5 is not high enough in order to, or not good enough in order to make actionable decisions. The kind of examples we have with anomaly detection are things like fault prediction. You may have a complex system and you're asking machine learning models, for example, to predict when a fault might occur, to warn humans, detect when a fault occurs to get a human's attention, and classify the fault, help direct the human on what is causing the fault and where it's occurring so that the issue can be addressed quickly. So there are many other examples of anomaly detection. For example, quality control. Defective parts are anomalous. And identifying the defective parts from the good parts, again, is an example of anomaly detection. And state-of-the-art is very similar in that accuracy rates typically top out at about 80%. Another example is predictive maintenance. In this case, instead of what we call preventive maintenance, for example, we replace a part every 1,000 hours or something like that. We instead can look for data and sensors on the part and predict when it will fail so that we can use a part for more of its remaining useful lifetime. So there are many applications of anomaly detection. This is a paper that UCLA published that looked at applying a quantum machine learning model to a predictive maintenance data set. And in this case, we have rotating machinery, and we're asking the quantum machine learning and the classical machine learning models to identify if there's a fault. And if there's a fault, what component is failing. We have the performance of the classical here compared to the quantum. You can see that the quantum machine learning model has a greater accuracy, precision, recall, and F1 score compared to its classical equivalent. And the accuracy improvements you can see are on the order of 7 to approximately 12%. Again, this is a great performance improvement. But a lot of people will, well, let me say that a lot of people are asking, why is this occurring? And do we know for which data sets there are these kinds of advantages? And the answer is that we don't know. This is an area of active research, but we do know a few things. One of the things that we do know is that quantum machine learning models can see patterns in data that classical machine learning models cannot. And so this was demonstrated by our company. And what we showed was for a particular data set, it's called the discrete log data set. It's used in cryptography. A classical machine learning model can see no better than a random distribution, whereas a quantum machine learning model can see a clear pattern with a sorting or classification rate nearing 100% accuracy. Now, this is for the discrete log data set. As far as I know, there's no practical application for this. This work has been generalized to data sets with group structure more generally. We're still looking for practical applications or practical data sets that have that kind of characteristic. And so what we're looking for are data sets for which a quantum computer has a greater inductive bias. And what I mean by inductive bias is the model is well suited for certain kinds of data distributions. So for example, what you see here is a linear model, this black line, naturally fitting to these points, which are all naturally arranged in a line. So a linear model has natural inductive bias for a linear data set. Similarly, this harmonic model or the sinusoidal model has inductive bias for harmonic data. If you're going to apply a sinusoidal or harmonic model to, say, linear data, you're going to have a lot of terms, which means that you're going to have a lot of data. So that explains the sampling complexity. And there's going to be problems with the fitting, and that would explain also the accuracy. And so we're looking for data sets for which a quantum machine learning model may have greater inductive bias. And a natural place to look is in quantum mechanical phenomena. And so we published these two papers where we, for example, looked at a quantum machine learning model with CERN. And we asked the quantum machine learning models and a classical machine learning model to predict this potential energy curve for a lithium hydride molecule. The black line is the exact solution. The quantum neural net is predicting these red crosses that lie on the black line. And the classical neural net is predicting these green stars you can see lie off the line. And as suspected, the quantum neural net performs much better than the classical net, probably because it may be because it has inductive bias for this kind of data. And you can see the root mean square error, RMSE, for the quantum neural network is over an order of magnitude better than it is for the classical neural network. Another example is work that we did with Mercedes-Benz. We performed materials informatics. This is a machine learning applied to materials. We applied a quantum machine learning model to predict the energies of batteries. Now, electric vehicles have some challenges in that the battery is usually the most expensive part of the electric vehicle. And the most expensive part of the battery is the cathode. And so there's a lot of interest in the industry to find cheaper and yet high-performing battery cathode materials. The materials tend to be very complex. And so applying some sort of quantum simulation of the material is quite difficult. We can't apply quantum machine learning to it. And so we took some quantum calculations for the energy, and we trained our quantum machine learning model here. And you can see that the match between the data and the prediction is very close. The R squared here is almost 0.99. And so again, the high accuracy here may be due to increased inductive bias for quantum machine learning for quantum phenomena. Okay, so you can see the state of the art, and you can see sort of the direction that quantum machine learning is going, and that we're looking for data sets for which quantum machine learning models have natural inductive bias. There are other characteristics of data sets that people have identified and are looking into. Quantum contextuality is one example. Quantum contextuality is a generalization of non-locality. And it may be useful for data sets, for example, for networks with conserved quantities. an example, lots of examples of that. One example might be, for example, might be a logistical network where your conserved quantity is a number of vehicles that you can use in order to deliver goods around your network. Okay, so that's quantum machine learning. Let me talk about the next area, which is optimization and search. Let me first talk about where the need is. Classical algorithms are good at this kind of optimization. The input space is smooth and continuous. There is one minimum. You may start anywhere on the surface and you're looking for the minimum here. And the typical algorithm used here is something called steepest gradient descent. And so in other words, you can stand anywhere here and you just basically look at where where it's the direction that's steepest, and you just follow that direction, and eventually you'll reach the bottom here. This works well for classical computers, and there's no reason for a quantum computer to try to improve upon this. What classical computers are not so good is this kind of optimization. The main difference is the input space here is discrete, whereas the input space here is continuous. And so there is no local gradient, or there is no steepness in order to guide you which direction to go in. And so the classical algorithm doesn't work. And the number of solutions to this problem, so this problem is the traveling salesman problem. And what you're trying to do in this problem is there are cities that a salesman needs to visit. What is the shortest path or sequence to visit those cities? And the number of solutions grows exponentially. And so you can't do a brute force search of every possible solution. And so this is an area where classical computers or this is the kind of optimization problem that classical computers find hard. So we're applying quantum algorithms to this kind of optimization problem. This kind of optimization problem is called combinatorial optimization. And an example of that kind of work is this paper that we published with Boeing. In this case, we're using carbon fibers to construct a wing. There are certain rules that have to go along when you construct this wing. For example, you can't have carbon fibers that run 90 degrees to each other, for example. They must be at 45-degree angles. So there has to be a certain sequence, but you want to set the sequence so that you're maximizing the strength to weight ratio, for example, for the wing. And so we've applied quantum algorithms to this problem. We've also applied quantum optimization algorithms to predict the folding structure for a protein. I understand my colleague will give a talk of this on more detail, so I'll let him talk about that. And then another example is this multi-objective routing and scheduling optimization problem that we demonstrated with Hyundai Motor Company. In this problem, what we have is a central depot D, and we're trying to schedule electric vehicles, EV 1, 2, 3, to deliver packages to customer 1, 2, 3. Along the way, there are the supply depots, S1, S2, S3, that these trucks may visit in order to recharge their battery along the route. So what we're trying to figure out is the routing and scheduling that minimizes the distance the trucks have to travel, the time it takes the trucks to deliver the packages, as well as the number of trucks used. And what we see is that as you increase the number of locations, the number of variables increases, and also the optimality gap increases. The optimality gap is the difference between the theoretical best solution and the solution that's currently being returned by the solver. You can see up to 15 locations. We need 400 variables. The optimality gap is pretty small, 0.003%. But once you get to 100 locations, the optimality gap jumps to 15%. And at 200 locations, this becomes an intractable problem. So where you start to see an advantage, or where a quantum computer could start adding value, is around 100 locations. If a quantum computer could, for example, find a solution that is 10% better or 15% better, you could potentially save a lot of time, gas, people, trucks, in order to complete these deliveries. What we see is that at 15% optimality gap, we need 14,000 variables. The way this roughly maps, is that you need approximately one variable per qubit. And so you would need 14,000 qubits here. Currently, our quantum computers have about 150 qubits, so we're still relatively far away. So we're going to need on the order of 10,000 qubits in order to start bringing value or finding solutions that are substantially better than what classical can bring. So this is the current state of the art. Where we see the direction going is in looking for hard but compact problems. And let me give you an example here. The traveling salesman problem that I was talking to you before. That's a linear assignment problem. And the largest problem size that's been solved for the traveling salesman problem is up to 25,000 locations. So classical computers can solve some fairly large problems. So that's a linear assignment problem. If we add another piece of information, say the flows, and this is a very typical problem. The common example is a facilities locations problem. Say you're planning a hospital or a medical campus, and you have certain distances between locations. For example, you may have the hospital here and the lab here and a surgery room here, for example. Um, and so you have distances, but you also have flows between those locations. You may have patients going from one location to another, doctors, medical supplies, medications, things like that. You have flows that are going from one area to another. And you want to optimize the location of these facilities such that you spend the least amount of time and effort. You minimize the number of flow transfers as a function of, as a product with distance. This is a much harder problem. This is called the quadratic assignment problem. And the optimal solution for this particular problem happens to be this, but the largest problem solved for this particular problem is only 36 locations compared to 25,000. So this is the kind of problem where we see quantum computers going in is looking for these hard but compact problems, problems that are small, and therefore can be represented on a quantum computer with, say, 100 or 1,000 qubits, but quite difficult still. Still of a size where a classical computer could not solve it. Okay, so let me go to, that is it. That is the end of my optimization section. Let me go now to the nearest application area, the closest that we believe where we have practical application, and that's in chemical and material simulation. One of the most exciting things about this field is that we often see the largest jumps in performance in products when we introduce a new material. And an example of that is flat panel displays. In some work that we're doing with Mitsubishi Chemical and JSR is we're looking at molecules that are used in these flat panel displays that have a higher power efficiency. Standard efficiencies are on the order of 25%. But what we're modeling with Mitsubishi Chemical and JSR are light emitters that have the possibility of 100% internal quantum efficiency. And this is important because, for example, the way we use our smartphones, we interact with our smartphones through our displays. The way most people use their smartphones, it is the display that is the highest power consuming component on your smartphone. And so you can imagine with a more efficient flat panel display, you could have, for example, a smartphone that lasts up to 4 times longer off a battery, or you can have smaller, lighter, cheaper smartphones because you need smaller batteries in order to have a smartphone that lasts, for example, for a day. So this is the kind of improvement we're talking about, a 4x improvement in power efficiency. Another example is batteries. You can see here in this chart the energy density of various battery chemistries. And you can see most of them are pretty small compared to gasoline. Gasoline is 10, maybe 100 times greater energy density than these batteries. However, there's this one battery chemistry, lithium-air batteries, that does have a energy density that approaches that of gasoline. Now, lithium-air batteries are still in the development stage, but one of the things we did with Mitsubishi Chemical is we modeled this reaction using our quantum computers. And you can see the exact solution here, this orange dotted line. And you can see the output from 2 of our computers, Amsterdam and Johannesburg. We name our computers after cities. And you can see the output of our quantum computers are quite close to the exact solution. So we're getting pretty close to this. But you can see the sort of potential of the kind of product and performance improvements we're talking about. Like with a lithium-air battery, we may see batteries that last 10 times longer. So instead of a battery lasting 1 day, it will last 10 days. Now, the current state of the art is that this algorithm called sampling-based quantum diagonalization. And what we're doing with this is that we're simulating chemistry or materials. And let me be a little bit more specific on what I mean by simulating material. What I mean is that we're solving the Schrodinger equation. That is this expression here. And if you're not familiar with the Schrodinger equation is the quantum equivalent of Newton's second law, which you may have learned from undergraduate physics, F equals ma. In fact, F equals ma can be derived from the Schrodinger equation. So this is quite a powerful expression. Now, what you need to know is that the computational complexity, or the number of computational steps, scales exponentially for classical computers, but only polynomially for quantum computers. In other words, it scales much more slowly for quantum computers. And so a quantum computer can model much larger, or solve the Schrodinger equation for much larger systems than classical computers can. So for those of you who are familiar with differential equations, this is a partial differential equation. We can separate the time component from the spatial component. So we get this simplification. This is called the time-independent Schrodinger equation. This is what we call an eigenproblem. We are looking for a set of eigenvectors and eigenvalues. It's a bit abstract as to what these mean mathematically, but the physical interpretation of them is that the eigenvectors correspond to the molecular orbitals of a molecule, and the eigenvalues correspond to the molecular orbital energies of a molecule. Now, we have now successfully applied this to this molecule, Fe2S6. This is a hard molecule to simulate for classical computers. One reason is because they contain transition metal atoms, and in this case, it contains iron. And for various reasons, these transition metals are difficult for classical computers to simulate. In this paper that we published, what we show are these results. And what we've identified are 3 eigenstates, A, B, C. Each of these lines is an eigenstate. And each y-intercept corresponds to an eigenvalue energy. And we can see for the ground state here, it corresponds to an energy that is very close to the state-of-the-art classical calculation, DMRG calculation, which stands for density matrix renormalization group. And so so the output from this sampling base, or SQD algorithm, is now matching the performance of the state-of-the-art classical algorithm. And because of the scaling, the fact that it scales more slowly for quantum computers, we believe that we can do molecules more complicated than this, which may be quite challenging for classical computers. Now, the way we did this is by combining a quantum computer with a classical high-performance computer. And we have now demonstrated this, for example, with Lockheed Martin, in order to demonstrate combustion chemistry for aerospace applications. We've also demonstrated this with Cleveland Clinic, who has applied it to modeling solvent effects in the life sciences and for medicine. An interesting story here is it took IBM about 18 months to develop the SQD algorithm. But once we figured it out, we taught partners that we're working with, such as Cleveland Clinic. And Cleveland Clinic was able to apply the state-of-the-art chemical simulation method within 3 months. And they published this paper, you can see in September, and we published our paper in SQD in May, so 4 months. Okay. So this is sort of the state of this is an overview of the use cases. You kind of start to see the business value that we're looking at. Things like use cases in life sciences, in the aerospace industry. I talked about batteries, I talked about displays, as well as a number of other use cases. Let me talk about the hardware. What we see here is our development roadmap. There are 3 layers here. You can kind of think of this bottom layer as the hardware layer. This middle layer is kind of like an operating system layer. This top layer is kind of a software layer, or software development layer. And then above this would be the applications layer. So we're here in 2025. We have the Heron processor working now. We actually have a 156 qubit version of the Heron processor already working. So we have 156 qubits available now. Later this year, we expect to offer quantum computers that have 1,000 qubits. And this is where we'll stay for the next couple of years. 100 to 1,000 qubits is a good range. It's a range in which it's above what classical computers can simulate. But and it's also in a range where the kinds of problems we want to solve, we're not typically limited by the number of qubits. We're typically limited more by the number of 2-qubit gate operations that we can execute. And that's the number that you see here in the parentheses. Right now, we can execute 5,000 2-qubit gate operations. maybe more in some cases. This is the most of any quantum computer in the world. And we'll be increasing this over time to 15,000 2-qubit gates in 2028. In 2029, what you see, let me blow this up in more detail, is what you see is we'll be able to go from 15,000 2-qubit gates to 100 million. So this is an enormous jump. The reason why we'll see this jump is because of a technique called error correction, which we'll be introducing in 2029. So we'll be able to do 100 million gates on 200 logical qubits. What this means is we expect the application space to suddenly jump. The number of applications enabled by 100 million 2-qubit gates over 15,000 will be much larger. And the application space will continue to grow as we into the future. In 2033, we plan to introduce a Blue Jay computer that has 2,000 logical qubits and can execute 1 billion 2-qubit gates. However, we do expect the first applications to arrive before 2029, before error correction. And we believe that error mitigation techniques in the sort of 10,000, 15,000 2-qubit gate operation will enable the first applications, probably in chemistry and material simulation. And at this point, the SQD algorithm is the lead candidate. Okay, so that is my last slide, and I am happy to take any questions. I guess if there are no questions, let me thank the audience for your time. And let me say congratulations on your Quantum Week at Yonsei University. Thank you very much.